Hello everyone and welcome back to another episode of FL Engineering, and today we're going to be seeing how much force the air would have on a 100-mile-an-hour basketball. So the first step is to import the geometry, which I already did. This basketball is 29.5 inches, standard size, but it doesn't have any grooves in it, which will affect the aerodynamics of it, but hopefully not too much. So the first thing we're going to do is we're going to use the geometry, and we're going to make an enclosure. And so this enclosure is basically like the airflow around it. So it's the simulated living, I guess, so like simulated room that the basketball is going to be flying in. So I think I'm going to make it a little bigger along the z-axis. So maybe -2. Actually, probably -6. And then you have to make it bigger the faster you go, because the more air it's going to affect around the basketball. And so think about it, if someone's going to be throwing a basketball, it's going to move a lot more air than it is going to be if some toddler threw a basketball, right? And this is just purely theoretical to see what would happen if someone could throw a basketball this fast, and how much force they would need to throw a basketball this fast. Alright, that looks about right for the basketball. So now we're gonna start the running, and now it's gonna run the simulation of the enclosure, which is again basically like the room or the air it's in. And so anything outside of this is non-existent. This is its reality. And so normally when I create a mesh, and I'll go over that later in the video, I would add boundary layers, but because this is just a quick test, I'm not gonna add any boundary layers, or, well, I'm gonna add boundary layers. I'm just not gonna add wake regions, refinements around the wake region, which is essentially when the air flows around the ball, air slows down in the back of the ball, and you have to refine the geometry behind the ball. But we're just doing a quick simulation here just to see what it looks like. And so now we can create a simulation from this, just like that. And so we're going to select the air material, which is, this is the air density, like probably around the, well, probably around, like, I'd say lower altitudes of New Mexico, maybe like, I don't know, 600 feet altitude, 1,000 feet altitude, somewhere around there. And then not very high altitudes. So for boundary conditions, we have to add the velocity inlet, which is essentially the direction the air is going to be flowing. So if you throw it one way, let's say you throw it from this side of the box to this side of the box, the ball is going to be flowing this way, so the air is going to be rushing the opposite way. Or if you think about it, in this simulation, the ball is stationary, but the air is moving at 100 miles an hour. Well, in reality, the ball is moving at 100 miles an hour. The air is still, but it doesn't matter. Same thing either way. So just to check which way is the front. So yeah, this is the front. So we're going to add the velocity inlet right there. And since it's along the z-axis, as you can see, this cube in the bottom right-hand corner is going this way. And so we can put it to miles per hour, 100 miles per hour. And then we can do pressure outlet, so 0 pascals, stationary air. Then we can add walls around the entire thing. These will be slip walls. So essentially what these are is telling that the air is just completely stationary around here, and these aren't like actual walls or anything. And so this simulation is just going to be someone throwing it outside, because I don't think you're going to be hypothetically throwing a basketball at 100 miles an hour indoors at a building. I don't think you're going to be throwing it that fast, but this is just for fun. And now for simulation control, we're going to run 1,000 iterations. So the way the computer does this is it runs multiple iterations, and it slowly gets a better solution every time. And so for the forces and moments, we're going to see how much force is acting on the ball just from the air. And so we can see, if we select this, now we have our forces and moments for this. And so next we're going to create a mesh. And so for this ball, I think we're going to do let's try a hex dominant mesh. And so this will take around probably a few minutes, and while we do that, I'm going to go over how the other stuff works. So potential flow initialization is just like so. You want to have this on because it slowly gets a better solution, but this will help it get a better solution faster. And then the right control time step, so every if these are the same number, it'll write a solution every single time. But let's say this is 500, it'll write a solution every 2 times. And the maximum run time is like, it takes a long time for a simulation to run, like not really long, but like maybe 30 minutes, 20 minutes. Probably this one won't take that long, but. And then the numerics, so once you get the values for velocity, pressure, and all these things for residuals, they will only go down to a certain number, and you can specify this number, and so they'll only get, I don't want to say accurate, but I do want to say accurate, so they'll only get this much accurate. And initial conditions are like again, the velocity, the air, like, so this is where you put in your wind, if you had any wind, right? And then okay, so mesh refinements, I'm not using any mesh refinements right now, but alright, so sorry about that, my mic cut out. Like I was going to say, the refinements, although I didn't do any right now, this would be like adding, so once you see when the mesh is done running, you're going to see little boxes, these tiny little boxes, and these are basically, the simulation checks the force on each of those boxes, and then it adds them all together and finds your solutions. And so refinements make more of the boxes, basically, and so you have more fine solutions, I guess. The meshing log, it just tells you all the also finalizing mesh, so it's almost done. So if we go up here, the actual geometry itself, now that the basketball is done, although you can hide the enclosure, inside of the basketball is actually nothing. And so all of this is air, and the inside of here is nothing, so it checks the nothing part as an object. So that's how that part works. And then you can click show all. And so now that the mesh is done running, Sorry, my cat is misbehaving. Okay, so here is the mesh I was talking about. As you can see, there's these little squares right here, and if I hide the selection, you can see the ball right here, and inside the ball is nothing. So there we go. And so it measures the aerodynamic force on the walls. Or actually, I can show you a mesh clip. And so if you click the mesh like this, it'll show you like an internal version of the mesh. So you can see like inside the ball and like outside the ball. And here are the little boundary layers right here. And then we can just add a y plus value just to check to make sure everything's accurate. And then once we're done with all that, we can start running the simulation. And yeah. Alright, and so now the simulation is done. As you can see, it's finished. It took 0.6 core hours and 17 minutes. And now you can see the forces and moments. You can see as they started going up, but they went up and down, but you can see there's still like a generally straight trend for these forces right here. And this is because the ups and downs is because if you look at the run, you can see that if you imagine the air flowing this way, there's a turbulent airflow where it switches like this in a triangular pattern. And so you can visualize this by adding something called a particle trace. Where you can simulate the ball, and you can hide all the other faces like this, so you can just see the ball. And you see the force on the ball. Like the red is higher pressure, because if you think about it, the air is hitting this part in the front when it's flying, and so it's going to be high pressure right here. But as it goes back, the air is just going to be flying past it, so it's not going to be as high pressure over here. And so if you look at the particle trace, alright, so now you can see the particle trace. You can see this is like the airflow over here, and you can do an animation by clicking animation button. And so it's important that you switch to particle trace, and then you can like speed up the animation or whatever, and so you can see the airflow around the ball and how it develops after that. And so you can see there's this giant part right here. This inner part here curves over the ball like that. And so if we go to the forces and moments, now that we've seen how the air flows around the ball, we can see that there's about 187 newtons acting on the ball. So you would have to throw it, so let's say 187 divided by 4.45, around 42 pounds to the force of the air would be around 42 pounds. So you would have had to throw it with a lot of force, like a lot of force to get up to the speed, and then to maintain the speed you need a lot of force. And so the acceleration is just going to be you're going to have to get it up to 100 miles an hour in an extremely small amount of time, and with air resistance and everything, that'll be super hard too. So thank you for watching, and I hope you enjoyed the video and learned something new. Make sure to hit the like and subscribe button, and stay tuned for more FL engineering. See ya.